Hi, it's Mr. Sad, and I'm going to talk to you now about half-life. Half-life is kind of like one of the most tricky things that we have to talk about in chemistry, simply because there's lots of points in which you can get confused. So let me talk about the first main idea of half-life, and it's pretty easy. I'm just going to define it right now. I'm going to define it in green because that's what we think of when we think of half-life. We think of radioactivity, we think of glowing, and blah, blah, blah. So here we go. Half-life. It's not a video game. Well, it is a video game, but I mean not in chemistry. It's not a video game. Half-life is the time it takes for half of a substance to radioactively decay. So what does radioactively decay mean? Okay, let's discuss that. So radioactively decay, what does that mean? When an element this is very slangy, spits out radiation. So, for example, when uranium does this, like we saw before, oops, like we saw before, it turns into thorium and 234. When this process happens, that is radioactive decay. When it's been spit out, this daughter element, the daughter element here, this is also a daughter element, but this what we typically think of as a daughter element, if there's one of them, that is the thing that has undergone radioactive decay. So here it started off as a parent element, and now it's a daughter element. Once it's changed from a parent to a daughter, then it's undergone radioactive decay. That kind of transition never happens in our lives. We don't go from parent to daughter. That's kind of weird. We go the other way around. We go from daughter to parent. But in radioactive terms, we go from parent to daughter. Once that happens, the element has said to be decayed, has been decayed. So let's just take this color scheme and go over here, and let's say you've got a bar of uranium. There's uranium. That's U-238. We don't have to put the 92 there. It's kind of redundant because we know it's 92 since it's uranium, but oh well. This whole thing right here is supposed to be green. Great. So that's at the beginning, and then let's say some time passes. The time has passed, and now half, it's supposed to be half of this bar is still, I mean, this is billions and billions of uranium atoms here, still billions of uranium atoms, but over here, this is 238 uranium. It has not decayed yet. It's still parent, but there's some parts of it that have. In fact, half of it has decayed. Is now this asparagus, they call it, color. I don't know if this is asparagus color. I think asparagus is a little bit more green. I don't know what asparagus the makers of Sketchbook eat, but this is not asparagus color to me. Anyway, this right here is a daughter element. Now this is a different element. This is thorium. Thorium-234. Again, it's 90. That's redundant, but oh well. So this right here is thorium-234. it has radioactively decayed. Where did the alpha particle go? I don't know. I don't care. This remaining part right here, that is thorium. This is uranium. It's gone and it's undergone 50% decay. So half of it has decayed. 50% has decayed. All right. So now we take this little example and we look at this definition. The time it takes for half of a substance to radioactively decay. So if this bar goes from here to half decayed, the time it took to go from here to there. I apologize about the construction that's apparently needing to go on in the background. The time it takes to go from there to there, that time, the delta T, the time that's changed from here to here, that is half-life. So if that is a year, then the half-life for this substance is a year. Let's look up what the half-life of uranium-238 is. I'm not sure off the top of my head. You say, let's look at a different tab. Uranium, oh my god. Uranium-238 half-life. Oh look, it's coming up. Half-life. 4.5 billion years. That's how long this takes. Wow. That's a long time. So that's a half-life for uranium-238. Half the time it takes for half this substance to decay is 4.5 billion years. It takes a while. All right. So that is what a half-life is. That's defining half-life. Now, if we want to make a little formula for this, we can do that. You'll see. Let's say, I'm just going to give you the formula. I describe in the text how to do it, but I'm just going to give it to you right now. So let's do a little formula. So for this, this takes, it takes whatever substance this is, and then there's half of it remaining. So if in these kinds of equations, what you're going to do is you're going to be using this equation right here. So you're going to say, okay, if I want to figure out the remaining amount, remaining amount of substance, if it's in grams, then that's great. If it's in kilograms, that's great. Just the remaining amount of substance, it's going to be a mass, equals the initial amount, and it's going to be in the same units, the same initial amount of substance times 0.5 raised to the power of how many half-lives there are. So the number of half-lives, say HL, half-lives that have passed. By. Okay, so this should make some sense. So every time you have a half-life, so let's say we go another 4.5 billion years here, think about what would happen to this bar. If you go another, so this is 4.5 billion years. Let's say this is 4.5 billion years again. Oh my god, what would happen to the remaining? Well, half of the remaining would be halved. Or half the remaining would be left. So instead of this, it would be like half of that. And the asparagus color would be 75% of this bar now. So this would be thorium, and the other part would be uranium remaining. It would only be 25%. So every time it gets halved. So if you multiply this by, if you raise it to the power of whatever number of half-lives you have, and then you multiply that by an initial amount of substance, that'll give you how much is left over. So let's say that this starts off as 100 grams. 100 grams after one half-life has passed, 50 grams are left. After another half-life passed, 25 has passed. So if we plug this into our equation, if the initial amount is 100 grams, now I'm using that color, times 0.5, and let's say that there are two half-lives that have passed. Well, then we put that as a 2 there. And now we're going to just put these numbers in and we'll solve the problem. So if you put those in, you're going to see that the final amount, the remaining amount of substance, is 25 grams. That's what's remaining. Okay, I hope this helped. Sometimes you need to figure out the number of half-lives. The problem kind of gives you another extra problem involved. Let's see if I can find a problem that has that. Yeah. So let's do this. Let's do the warm-up. The warm-up is actually not that easy. So I'm looking at warm-up number 1. And warm-up number 1 says palladium 100 has a half-life of 3.6 days. So we know the half-life of this. I'll make a little line here to distinguish the two. Oh, I want to zoom out. How did I go in? I wanted to go out. Shoot. Zoom. Zoom out. Can I zoom out? Zoom. No! Shoot. I think I went like this. No. I don't know what I did. Anyway. Okay, so we've got palladium. Its half-life is 3.6 days. Now that's not the number of half-lives, that is the half-life. So we don't know how many half-lives have passed. If we had 6.02 times 10 to the 23rd atoms, so that's our starting point, our initial amount is 6.02 times 10 to the 23rd atoms. The question is, how many atoms will be present after 20 days? So our time that has passed equals 20 days. So the first thing you need to find here, since we know the initial amount, we got that. This is a constant. We don't know this. That's our question. We can figure this out here, the number of half-lives that have passed by. Now, how do we do that? Well, we take the time that has passed, so it's 20 days, and we know that there is one half-life every 3.6 days. So if we put this little conversion here, we cross off our days, and we're going to see that 20 divided by 3.6 is, oh my god, I don't know off the top of my head. 20 divided by 3.6 is 5.55555. 5.55556. Okay, so that's the number of half-lives. That's the half-lives. So it's 5.55556 half-lives. Great. So now we can plug this into there. That's how many half-lives have passed by. So let's put all of our information into our equation here. So the initial amount of substance is 6.022, which is 12. 6.02 e to the 23 times 0.5 raised to the 5.55. Let's just call it 556. Okay, and that's going to get us our remaining amount of substance. So if I put this into my calculator, and sometimes it's difficult just to put this into my calculator. I'm going to do a two-step calculation. I'm going to do 0.5 raised, and I use a little caret that's above the division sign, raised to the 5.5556. Okay, I get an answer of 0.02126 something. I'm going to take that answer and I'm going to multiply that by 6.02 e to the 23. E to the 23. And I'm going to get as a final answer, there it is. The final answer is 1.2. And I'm going to use sig figs here. There's only 2 sig figs, so it's going to be 1.3 e to the 22 atoms remaining.